Alright, so welcome back for section 14.4. And on section 14.4, we're going to be talking about tangent planes and linear approximations. Alright, now if you recall from section 12.5, we had the equation of a plane. The equation of a plane was ax plus by plus cz is equal to d. And d we're able to extract from some coefficients that were made up of the normal component of that tangent plane and a point on that plane. Alright, so we could have easily written it this particular way: a times x minus x naught plus b times y minus y naught plus c times z minus z naught. And if we were to write it this way is equal to 0, if we were to write it this way, then we're going to be able to explore this just a little bit more. All right, so this is the way that I want to write it, and that's the way that I want to work with this particular case. Now, the reason I want to work with this is because in this form, what I want to do is I want to divide both sides of this equation by c. All right, so here's a c, and I'm going to divide both of those sides by c. So let's go through this. I'm simultaneously solving for z minus z naught to see what we get here. There we go. Just like that. Alright, so what I did was I isolated the term c times z minus z naught, and then I divided both sides by c. That way I could get z minus z naught is equal to this particular case. Alright, now what I'm going to do at this point in time is I'm going to make a substitution really quick, and I'm going to say let a equal negative a over c and b equal negative b over c. Now, in doing so, this is going to simplify a few things, and you're going to see why I want to do this. There we go, plus b times y minus y naught. There we are. Now, in doing so, I simplified this just a little bit more. My coefficients are no longer coefficients that are rational coefficients. At this point in time, they're just a and b, and we're going to figure out what those a and b values are. All right, so let's go ahead, and at this point in time, I want to fix one of my variables. All right, so let's go with the fixing of a variable. So I'm going to assume here that x is equal to x naught. Now, if x is equal to x naught, then one of the things that we get to see happen here is that z minus z naught is equal to b times y minus y naught. And the reason this occurs is, again, because this a times x minus x naught, if they're the same value, then that just cancels. So here, we're actually left with this really nice result. And I want to pause here for a quick second. I want to look at this result. This result tells us that my coefficient of b is actually equal to z minus z naught divided by y minus y naught. Now, pausing here for a second and looking at this, this should kind of remind you of the slope, right, from algebra class. That y2 minus y1 divided by x2 minus x1 kind of reminds you of that, and it should, because that's exactly what it is. But in this particular case, this is actually looking at the rate of change in the z values with respect to the y values. In other words, would you be able to agree that this rate of change is actually the definition that we have for a derivative? Well, sure is, right? So the coefficient for b, according to this, is that it depends on the function for z. So the function for z we're going to assume that at this time, let's see, we're going to say let z is equal to f of xy. And if this is the case, then b coefficient is the partial of that function with respect to y at that ordered pair, x naught, y naught. Nice. So what we get here is something really, really nice, that we actually get to see what the b value is, and if we take the exact same approach for the y values, that we fix the y values, then we get that the a value will be something very, very similar to this, in the sense that the a value will now be the partial derivative of the function with respect to x evaluated at that initial point x naught, y naught. Which then tells us that using all of this information, so using this information, we're now going to be able to extract that z minus z naught is equal to, well, the a coefficient is now f with respect to x at x naught, y naught, and that's multiplied by x minus x naught plus the b coefficient, which was the partial of y at x naught, y naught, multiplied by y minus y naught. And that's what we wanted to see, because now, as you saw from the very beginning, the equation of the plane now becomes this equation so long as we're able to extract what the function is and its partial derivatives. So I'm going to write this really quickly as a definition, that way we can formally work with it moving forward. All right, so I'm going to fill in the definition really quick, so just bear with me. All right, so here's your definition that says, suppose f has continuous partial derivatives. An equation of the tangent plane to the surface z is equal to f of xy at the point P, which is given by x naught, y naught, z naught, is this equation that we derived up top. All right, that's the derivation that we got there. Now, how does this look like in terms of visualization? Well, to that I turn to my old friend GeoGebra. So here what I have is a surface, right? This is the blue surface that I'm looking at. I fixed a point, or let's just say I put a point, point A on this surface. Now you see here a purple plane. That purple plane is tangent to that surface at that given point. Now I've constructed this so that anytime that I move my point, then that tangent plane is going to always be tangent to that particular surface. And you'll be able to see that there. So, one of the questions, or one of the reasons I like to look at this, is because there's this large concept that actually a good portion of, let's say, humans believe that the world is round, or sorry, that the world is flat. Now, why do they believe that the world is flat? Well, generally speaking, if we fix a view at one specific point on a given surface, let's take the Earth for example, and we construct a tangent plane, the tangent plane is this flat surface. So when you stand at one particular point, or when you stand at one specific view at this surface, then all you get to see is this flat surface, which is a plane, right? And that's essentially what they're looking at. So when flat earthers say, oh yeah, the world is flat, well, you haven't exactly taken multivariable calculus yet to determine that, you know, you're standing at one point and all you're doing is you're linearizing your view, and that's it. And we're going to talk about more of that fact of linearizing in just a little bit. All right, but for now, let's go back to an example. All right, so here's the example. We want to find the equation of the tangent plane to z is equal to the natural log of 2x plus y at the point -1, 3. Now you're going to notice the point that is given to us, the point is only given in the domain of the function. So we then need to extract what the point is going to look like in R space 3. So that's going to be one of the first things that we do, is we want to find that point in R space 3. So let's go through it. We're going to take z and we're going to evaluate this at x is equal to -1 and y is equal to 3. Therefore we get the natural log of 2 times -1 plus 3, which is just the natural log at 1, which is 0. So the point that we're looking at is -1, 3, 0. Awesome. Now we want to talk about the partial derivatives. So let's look at the first partial derivative, the first order partial derivative for that function. So let's look at the partial of the function, and actually, you know what? I'm going to rewrite this differently. I'm going to say z is equal to f of xy. Whoops. Let's trash that. There we go. F of xy, there we go, is equal to the natural log of 2x plus y. There we go. Now when I look at the partial derivative with respect to x, we take the derivative of the natural log. Derivative of the natural log is 1 over its argument, but chain rule says that we take the derivative of the inside with respect to x. That means that we're going to get 2 divided by 2x plus y. We take the other partial derivative for the function with respect to y. Taking that partial derivative with respect to y, once again, partial derivative, or in this case derivative of the natural log, is 1 over its argument multiplied by the derivative of the inside, and that's with respect to y, which is just going to be 1. Now I want to evaluate the partial derivative at the given x and y values. Now, evaluating the partial derivative at the given x and y values, I just got to make my substitutions here. So the argument, the denominator down here, once I make these substitutions, that should get me a 1, so this will be just 2. The partial derivative with respect to y, evaluated at -1, 3. Again, that denominator is going to be 1, so that just gets me a value of 1. So finding the equation of the tangent plane, alright, so the equation of the tangent plane that I need is z minus z naught is equal to f partial of f with respect to x, evaluated at x naught y naught, multiplied by x minus x naught, plus partial of f with respect to y, evaluated at x naught y naught, multiplied by y minus y naught. There we are. Now making the substitutions for what we know. Z minus Z naught. Z naught is actually given here. This is Z naught. Alright, which is 0. So Z minus 0 is equal to the partial derivative evaluated at x naught y naught, and that's going to be 2, times x minus x naught, that's going to be plus 1, plus partial of y evaluated at the point, that's going to be 1, multiplied by y minus y naught, which is y minus 3. There we are. Which means that the equation of the tangent plane that we get to see here is z is equal to 2x plus 2 plus y minus 3. Alright, now this actually gets to simplify a little bit further. And let's get all the variables to one side. So I like getting everything to the left side, so let's say 2x plus y minus z. So 2x plus y minus z should be equal to 1. There we are. That is our final answer. So if we then went to GeoGebra and we said, hey GeoGebra, what I want to do is I want to graph this equation first, and then I want to identify this point here, and then I want to identify this plane here, then GeoGebra would graph this first function, then you would identify this point, and then you would see that this tangent plane goes through that given point and is tangent to that specific surface. All right, so this is how we want to work with this particular set of equations of tangent planes. All right, now that we have more of the basis for it, let's start talking about that linearization that I mentioned earlier. So if we want to talk about a linearization, that means that we want to approximate, or we want to linearize a function in terms of a tangent plane, or in terms of a plane. So imagine taking a sphere, imagine taking this hyperbolic ellipsoid, focusing only on one point, and then figuring out what plane is tangent to the surface at that one point. Therefore, you're going to create a surface that is a plane that will be able to model that given function as long as we are near that given point. So, let me give you a quick definition. Excuse me here. There we go. Multiplied by y minus b. There we are. So here is your tangent plane approximation for the function. The tangent plane approximation says that if we want to approximate our function, then all we need to do is figure out what is that tangent plane approximation, all right, or what is the equation of that tangent plane. Now, that equation of the tangent plane we actually have from above, and I'll point it out in just a little bit. All right. Now, typically we have a linearization. The linearization is given by this exact value of the tangent plane. So knowing that the tangent plane approximates the function, we use that approximation to call it a linearization. So we want to work with the linearization for this particular section. All right. Now, looking at this piece here, all right, looking at this piece here, whoa, that did not come out the way I wanted it to. Let's say, no, I don't want to do anything there. All right, let's say I go here, and let's go there. There we are. And I want to copy this, and let's move it down here. Let's see how this works. Whoa, what just happened there? You know what? Technology is not my strong suit. And we can see why. There we are. Wow, look at that. It actually worked for me. Okay, great. So let's start dissecting this. All right. So looking at this equation for the equation of the tangent plane that we initially derived from the very beginning, what would happen then if we then start solving for z? Well, if we took that approach to start solving for z, in other words, to start solving for the function in question, then we're able to see that at this point in time, these two equations are the same. Yay, they're the same. Which means if they're the same, then all we're doing is we're using a manipulation of the equation of the tangent plane to get us that linear approximation, or in other words, that linearization. So let's look at an example for this linearization. So here goes your example. Find the linear approximation to z is equal to 3 plus x squared over 16 plus y squared over 9 at the pair -4, 3. Now again, we want this linear approximation. Another name for this linear approximation is that we want to find the linearization. So if we want to find the linearization, then again, we need to explore a few options here. All right, so number one, I'm going to say that z is really just a function in terms of x and y. That way I can work with and extract what I need. All right, so forecasting, I kind of need to know what is the z coordinate. In other words, what is the ordered pair or the ordered triplet that I'm looking at in R space 3. So let's start looking at that. I'm going to have here that I have a function of -4, 3, and I'm going to make those substitutions. 3 plus here is going to be -4 squared over 16 plus 3 squared over 9. You're going to see the two terms, the two rightmost terms, they're just going to be 1, so it's going to be 3 plus 1, which is going to be just 5. Nice. So this is, again, that function or that z naught variable that we're looking at, or sorry, variable constant that we're looking at. So now let's look at the partial derivatives. Let's find the partial derivative for the function with respect to x. So the partial derivative with respect to x, that's going to be 2x over 16. 2x over 16 simplifies to be just x over 8. Partial derivative with respect to y would just be 2y over 9. So that's going to be 2y divided by 9. Making my appropriate substitutions. Partial with respect to x at -4, 3. This is going to be -4 over 8, which will get us -1/2. Partial with respect to y at the point -4, 3. All right, making our substitutions here. So y value would be 3, so that's going to be 2 times 3. That's going to be 6. 6 divided by 9. 6 divided by 9 simplifies to 2/3. Nice. All right, once I have this, I have everything for my linearization. The linearization in terms of x and y is going to be that function value that we found, f of ab, plus the partial of the function x at the point ab multiplied by x minus a, plus the partial of the function with respect to y evaluated at ab multiplied by y minus b. So let's make those substitutions. Linearization, or in other words, this linear approximation. The function evaluated at AB, that was 5. Partial derivative of f with respect to x evaluated at AB, that was -1/2. So let's go with -1/2 here. -1/2 multiplied by x minus a, which is -4, so that's x plus 1/4. Sorry, x plus 4. Plus partial of f with respect to y evaluated at AB, that's 2/3. That's 2/3 multiplied by y minus b, which is 3. and here is our linearization. In other words, here is our linear approximation. So again, if we go to GeoGebra and if we say, hey GeoGebra, what I want to do is I want you to graph this function. You're going to be able to graph it. Then I want to select this point. Okay, that's fine. But instead of selecting that point, I would rather select this point on GeoGebra here for that point to be the point -4, 3, 5. Putting this point on GeoGebra would then, once we go through and graph this plane, z is equal to all this, we're going to be able to see that this plane here is tangent to the initial function at this given point. And that's the linearization, or the linear approximation, that we want to work with. All right, so those are linear approximations, and those are tangent plane approximations. Now let's see if we can calculate some differentials. All right, so total differentials now. So really quickly, what I want to go back and do is I want to talk about this equation here that we derived. Now, looking at this equation where we derived, we want to talk about this using differentials. Now, look at this piece here, this piece, and this piece here. Right? The first piece is just talking about the difference in between the z values. In other words, we're looking here at some sort of delta z. The second piece here is kind of like looking at some delta x, and the third piece here is kind of like looking at some delta y. Right? We're just looking at some differences in between these x, y's, and z values respectively. Now, when that happens, we can talk about a total differential being, in this particular case, dz being equal to the partial derivative for the function with respect to x evaluated at x0, y0 multiplied by dx plus the function with respect to y multiplied by, evaluated at x0, y0 multiplied by dy. And this right here is what we consider that total differential. That total differential will then be able to calculate what is, see, I can't write and talk at the same time, but it's okay. Differential, there we go. The total differential is going to calculate the total displacement of the function. If we calculate the total displacement of the function, then that's going to give us a way to be able to identify by how much are all of these functions changing at the given points that we want to observe them at. All right, and that's going to be it for this section. All right, so there you are, total differential, tangent planes, and linear approximations to these given functions or these given surfaces.